In 1968, on the narrow streets of Monte Carlo, someone quietly added 2 small winglets to a Formula One car. They were barely noticeable. No one expected that this single experiment would permanently change the speed limit of Formula One. From that moment on, F1 truly entered the age of aerodynamics. In the early days of Formula One, power was everything. Engine displacement and maximum RPM decided how far you could pull away from your rivals on the straights. Teams pushed horsepower to the extreme. Engines failed, gearboxes broke. Back then, the world champion wasn't the fastest car. It was the one that survived to the finish. Then, Graham Hill took pole position and won the race in a Lotus fitted with small wings. From that moment, Formula One history was rewritten. The core competition of F1 shifted from pure mechanical strength to a war of engineering and physics. For a racing car, it mainly comes down to 2 forces, drag and downforce. Drag means the faster you go, the more the air resists you. Air piles up in front of the car, forming an invisible wall. This force slows you down and demands more power from the engine. Downforce is what racing cars truly crave. By shaping the car in specific ways, engineers control how fast air flows over different surfaces. Slower air creates higher pressure, faster air creates lower pressure. This pressure difference pushes the car onto the track, increasing grip and allowing higher cornering speeds. In simple terms, drag pulls you back, downforce presses you down. Without downforce, modern cornering speeds would be impossible. At just 150 kilometers per hour, an F1 car already generates downforce close to its own weight. At top speed, that figure can exceed 5 times the car's weight. In theory, an F1 car could drive upside down on the ceiling. But downforce is never free. Bigger wings create more grip, but they also create more drag. This is the fundamental contradiction of F1 aerodynamics. More downforce means faster corners. More drag means slower straights. Engineers spend countless hours chasing one goal, to generate as much downforce as possible while adding as little drag as possible, finding the absolute limit between the two. Cars don't need the same downforce everywhere. It depends on the circuit. That's why teams change wing configurations from race to race. On tracks like Monaco or Hungary, maximum downforce matters most. On Monza or Baku, low drag and top speed decide everything. But aerodynamics introduced another problem: dirty air. When 2 cars run close together, the leading car creates turbulent airflow behind it. This disturbed air severely reduces the efficiency of the following car's wings, causing a sudden loss of downforce and grip. The driver behind is forced to choose: slow down early to stay safe, or carry speed and risk understeer or oversteer. Unless the chasing car has a clear advantage, staying close on corner exit is extremely difficult. As wings became more complex, the dirty air problem grew worse. After many attempts, the FIA chose a direct and controllable tool. Introduced in 2011, DRS was never meant to punish the leader. It simply compensates for the performance lost while following in dirty air, and as this season ends, DRS itself will leave Formula One. So, is there a way to gain massive grip without a huge drag penalty? Yes, ground effect. Ground effect works by shaping the floor into venturi tunnels, forcing air to accelerate between the car and the ground. This creates a low-pressure zone, like a giant vacuum, pulling the car onto the track. Compared to wings alone, ground effect delivers cornering grip with less straight-line compromise. That's why, after the 2022 rule changes, F1 re-entered the ground effect era. It's called a return because Lotus had already mastered ground effect in the late 1970s. Those cars cornered at unbelievable speeds, but if the floor stalled, control could vanish instantly. For safety reasons, the FIA banned ground effect in 1983. Today, it has returned, but under strict limitations on floor design and dimensions. This year marks the end of the ground effect era once again. From next season, Formula One enters the era of active aerodynamics. Flatter floors, smarter wings. Cars will no longer rely solely on ground effect to generate performance. In reality, modern F1 aerodynamics extend far beyond wings and floors. Almost every external surface interacts with airflow, and all of it must be validated through CFD simulations and wind tunnel testing. CFD can be understood as a virtual wind tunnel. Teams simulate airflow on computers to evaluate aerodynamic efficiency, but no matter how advanced the simulation is, it remains a model. Only wind tunnel testing with a real car reveals real airflow behavior. To control costs and ensure fairness, the FIA limits CFD usage and wind tunnel time for every team. These limits are not equal. They are based on the previous season's championship results. Top teams receive less development time, while lower-ranked teams receive more. Each June, the FIA recalculates these allowances based on the first half of the current season, giving struggling teams more development time in the second half. Aerodynamics make cars faster and racing more intense, but every approach has a cost, and the cost of aerodynamics is danger. Its greatest risk lies in how it fails, not gradually, but suddenly. Downforce exists only within a very narrow aerodynamic window. Car attitude, ride height, and even suspension compression must all remain within precise design limits. If any of these variables are disrupted, a lifted nose in a high-speed corner, the floor briefly touching the ground, or turbulent air while following another car, flow separation can occur and downforce can collapse in an instant. This is not a loss of performance. It is a loss of grip. For the driver, it does not feel like the car has slowed down. It feels as if the ground has vanished. The steering is still there. The brakes are still there, but the tires are no longer pressed into the track. Without warning, the car becomes unnaturally light, and high-speed loss of control often follows. Such failures are not rare in Formula One history. That is why aerodynamics in F1 have never been only about speed. They are an engineering discipline that exists alongside the edge of control. The engineer's job is not simply to generate more downforce, but to ensure that when the air turns against the car, it does not immediately turn against the driver. From Colin Chapman's early wing innovations to today's precise FIA restrictions on CFD and wind tunnels, aerodynamics in Formula One have followed a long journey. Every technical shift is a search for balance between speed, downforce, drag, and safety. Modern F1 is no longer defined by speed alone. It is the result of technology, strategy, and intelligence working together. The circuit is not just asphalt. The real track exists in the invisible air above it, and whoever shapes that air controls the race.